I'm going to talk at the beginning about a very specific example. It's a physics example where we have a problem to solve, and the solution to the problem I will show you first with a guess, then I will give you a general formulation of the problem of transferring information from measurements to a model of the source of those measurements, and discuss some algorithms for actually implementing that transfer. And that's what we've all called data assimilation here. Just as a contrast, with the exception of now, I will not say the name of Kalman. I will not linearize equations. And I will not assume Gaussian distributions. Because the models that we deal with, in all of the things that have been said, but explicitly in what I'm doing, the neuron models that correspond to what Margoliouth talked about, my first example, are all problems in nonlinear physics, and none of those previous qualities apply. All right. I'm at the University of California in San Diego, both at the Department of Physics and the Scripps Institution of Oceanography. And I'm going to move on now to the first. Well, let me try that. I noticed that if I do this, you can see the laser pointer light on this screen, but not on those other screens. So do you have a meter stick? Do you have a physical pointer? Nope. OK. Then I'll just go to the board. All right. I'm going to try to give an introductory talk and, at the same time, an advanced talk. I hope by the end of the afternoon, besides being exhausted, you'll see that the techniques I'm talking about are not limited to meteorology. They're not limited to physics. They're not limited to biochemistry. They encompass all of those problems, cast appropriately in the context that I described, taking data, developing a model in the case of the first parts of the talk based on the biology, the biophysics, the physics, the geochemistry, whatever. In the case of the latter part of the talk, where I show you that everything that we have done and heard today and in the rest of the earlier part of the week are all the same problem as the machine learning problem, which is very exciting. And I believe that what we have talked about here this week will uncover why that effort has been so successful, and therefore good for all of us. And I hope you ask a lot of questions. That includes not only Sebastian, but everybody else. Okay? Have I said anything wrong yet, Sebastian? No, not yet. Okay. I'm sure I'll hear about it. All right. So picking up from Dan Margoliouth's talk, I'm going to talk about electronics. And here's my story. As a New Year's present, I got a transistor. Not everybody would think that was much more than the piece of coal that Charles Dickens' characters got for Christmas. But I'm really excited because I want to build the follow-on computer to the K computer, and I want to build it out of the transistor I got as a New Year's present. And I want to know what's inside that transistor. Because I want to know, when I put a lot of them together into a network that we call a machine, such as the K computer and its follow-on, how they all work together. And it's better to know how they work individually. It's exactly the problem that Dan Margoliouth talked about, except his transistors were called neurons. Our transistors are not alive. He emphasized that cells are alive and much more interesting than transistors. But they had to be put together in networks in order to perform functions, which is what developing nervous systems is all about. It's exactly the same problem as studying the atmosphere and the ocean. You have data. You have a model. Its foundation, as with the transistor it happens, is well grounded in physics. It's in the fluid dynamics of the problem. The boundary conditions are unbelievably complicated and horrible. And the forcing function is known, we usually call it the sun. And there are all sorts of transfer functions of the light from the sun to energy sources used in the motions of the atmosphere and the ocean. All these problems are identical. They require data, they require a model trying to describe the origin of the data, and they require methods in order to make the transfer from the model, from the data to the model. I will emphasize all of those points. All right, here's my transistor. So what am I actually going to do? Here's my general answer. I'm going to take the transistor and I'm going to put it in a circuit whose characteristics I know. So this is going to be a standard linear circuit of the kind that I suspect most, if not all of you, have studied in an elementary physics course. How many of you ever studied linear RLC circuits in a physics course? How many of you have not ever done that? Okay. You've never taken a lower introductory physics course and had a laboratory in electronics? Well, listen carefully for a bit, and if I don't address your questions, have you ever owned a radio?
Yeah.
Good, then stay. Right. All right, so what I'm going to do is I'm going to put my transistor into a circuit, some of whose properties I know. I'm going to put a voltage across the circuit or inject a current into the circuit to make it oscillate. Those oscillations of voltages and current will propagate through the little circuit I made, and then I will collect data from that circuit. I will then ask, how does the model respond when I put the same currents into it? Thank you very much. Here, I trade you. Okay. I'm going to ask, how does the model behave when I drive it in the same way? So I'll get an output, which I will call the model output. And I will have some data of how the actual transistor works. And then I will ask that the data that comes out of out of the transistor being driven and the voltages, in this case I'm talking about, out of the model, I want to know how I make them as close as possible. So I synchronize my model, which has parameters in it that I wish to learn, with the data which I've gotten by doing an experiment on the system, subject to the equations of motion. So I'm going to minimize this with constraints. And then I'm going to test the model, because as you'll see, my transistors doesn't work with voltage alone, with the standard circuit equations that I'm sorry you don't know, but they are basically a statement of conservation of current. I think you'll probably accept that. That with those equations, which are derived in the 19th century, we will have 3 independent variables in this particular circuit, not 1. So the data comes from driving the circuit and measuring one of the 3 parts of it. The model I know everything about, but I only can compare the model output of voltage with my measurements. And I still have to make this as small as I can. And I have to figure out how to measure, or excuse me, estimate accurately what I don't measure. Now that should sound pretty familiar. Think about what Dan was talking about. He has a neuron. It has a lot of components. He described the sodium component and the potassium component, and I mean, you saw his list. It was pretty long. But if he can only measure the voltage when he pushes the neuron by putting current into it, he has to determine how all of the ingredients of that model work, the unobserved variables, the parameters that he doesn't know, by somehow doing something that I'm going to do here. That's the job that we face. When I'm done doing the minimization so that my model is producing a voltage, for example, that's very close to the data, and you can decide what level of accuracy you want. I still don't know whether the model is correct. What I have to do is I have to take the data away, which is a learning or instructional aspect, put a new driver into the model, a new current, or in our case, a new voltage, and measure the response of my model and compare it to what the actual device does, my transistor. So I have to use it to predict the future in order to validate the quality of my model. If you think about the scientific problems that we talked about, never mind the techniques, never mind localization or some other mathematical this or that. That's what we're all after, is to verify the quality of a model that we use to describe a complicated behavior where we have measurements that are sparse, typically fewer than the number of measurements we can, than the degrees of freedom of the model itself. And the validation of the model is the prediction. So let me translate that into common jargon. Getting a good fit to your model is great. Congratulations. It tells you that your model is consistent with the data, but it doesn't tell you anything about the quality of your model. All right, so what do we do? All right, this repeats what I've said. I may or may not show this slide many times, but this is what you have to do. I will also show you near the end of the talk that in the present practice of machine learning, this is what they do. And the tools that have been described earlier this week and that I will describe give an insight into what is typically the machine learning black box on how it actually works and how you can choose from the exercise that's called machine learning and this method and that method, the model that is organized by the data, trained by the data, that gives the best predictions. Okay. After all that talk, here's my transistor. B, C, and E are transistor names. You have to have names for things. This is not ENSO or whatever it is, you know, ensemble common filters or anything. This is the collector, the emitter, and the base of pieces of semiconductor material that were put together to make a device that's a switch. You put in some voltage, and the current switches from flowing into direction A to flowing into direction B. It acts as a decision maker that's voltage dependent, and that's the basis for all of the computers that we have. It's a fast switch. This is the only piece of the circuit that isn't understood from the 19th century. Here I have a resistor. The voltage through it is Ohm's law. It's the current times the resistance. That's it. Here I have an inductor. The voltage through this inductor is the current times the time derivative, the inductance times the time derivative of the current. 19th century, all charge conservation. Here's a capacitor. The charge on the capacitor is the voltage times the capacitance. The current is the derivative of that charge, current per unit time. And that gives rise to these equations, known as Kirchhoff's equations, again for the 19th century. The only thing that we don't know in the Kirchhoff's equations are the current coming from through the collector. That we have to model the transistor in order to represent what this nonlinear device is doing to our currents. We also don't know the current through the base. And so we have to give a model of these two currents that are based on some idea that we have about the physics of this little piece of solid-state material. Well, we're not the first people to think about that. This problem has been solved and studied and solved forever. The longest living model that I could find was invented in 1954, and a slightly more elaborate superset of that model was invented in 1970. And we're here in the well past the 1990s. We're 20 years, almost 30 years past that, and we're still studying this little circuit. This little circuit has a name. It was invented by a British electrical engineer named Colpitts in the 1920s.